Good afternoon, and welcome to our live stream of Tour of the Universe from Morrison Planetarium. My name is Ryan White. I'm the Senior Director of Morrison Planetarium and Science Visualization at the California Academy of Sciences, and I'm going to be your host for today's tour. Now, most often when we do this tour, it's a simulcast from Morrison Planetarium itself. Today, I'm actually coming to you from home, and unlike the simulcast where you're listening in to what's happening in the planetarium but can't interact with the presenter, at least for this week and next, along with some of the weeks prior to this, you can actually ask questions if you find something interesting along this tour of the universe, and put those questions in your in chat, either on Facebook or on YouTube, and it's possible those can be relayed to me so I can answer them in the course of the program. That said, what I'm going to be doing, and you won't need to see me for most of the program, is taking you along a tour of our virtual model of the universe. This is a three-dimensional collection of objects and locations in the universe assembled with rigorous scientific accuracy to put everything in its right place. And we're actually starting our program at the International Space Station. So we have been kind of floating along with it in the few minutes leading up to the program here. And this is a great place to start our program because it's sort of human scaled. And we're going to be traveling so far out into the universe in the next 20 minutes, 30 minutes, that it's nice to start at something that is kind of easy to grasp in terms of its size. The ISS, or International Space Station, is about the length of a football field, give or take, and it doesn't actually even matter if you're talking about American football or soccer. It's the 100 yards or so, or 100 meters. And if you can imagine, inside these capsules, you have astronauts who are hard at work, traveling in orbit around Earth, and doing the research and increasing our understanding of how humans can operate in space. I'm pulling away from the ISS now, and it kind of looks like it's plummeting down into the ocean, but that's not really what's happening. It's just that we're pulling it far enough away that we're seeing it recede into the distance. And actually what I'm going to do is add an orbit line, so you get a sense of the trajectory of the ISS around Earth. And what's interesting to note here is that this is as far as humans travel out into space these days, a few hundred kilometers, a few hundred miles above Earth. And as we travel farther from home, what you'll see fade up is a patchwork of satellite images that are about a day old. This is what Earth looked like roughly 24 hours ago. And we page in that satellite data as quickly as possible, and then use it to map what Earth looks like from day to day. And so you'll see that it's kind of incomplete. You'll see seams here between satellite images that are taken at different times, and you'll see that there are limits to how far the satellite imaged toward, in this case, the North Pole. If you're good at geography, you might recognize the Baja Peninsula here, California. So in fact, ISS traveling overhead, actually ISS is in its position from about a day ago, so it traveled overhead. But this is indicative of the kind of data that we bring into our model of the universe. It's just that this happens to be terrestrial data, whereas most of the data that we'll be looking at today is astronomical or celestial in nature. So what I'm going to do is continue to pull away from our International Space Station. You can see the lights of North America down here, representing the nighttime side of Earth. And as we pull back, what I'd like to do is really try to give a sense of the scale of the universe around us. You can see our starry background. If you're good at constellations, you might be able to pick out some constellations. But what I'd like to talk about is sort of the three-dimensional perspective on the universe that we're going to get. And to do that, let me go ahead and actually add some more diagrammatic elements, a little bit like that ISS orbit that's now receded into the distance. What I'd like to show you are the trajectories of the planets in orbit around the sun. So this line that you see kind of coming up to Earth is the trajectory of Earth as it makes its annual trip around the sun. As we pull far enough away, you'll actually also see an orbit around Earth which is the orbit of our moon. So the moon is about 240,000 miles away, about 400,000 kilometers on average. So if you want to imagine how far that is, like if you had a car for a really long time and drove it pretty consistently, you might put 200,000 or 250,000 miles on it. So if you can imagine driving a car over its lifetime, all of the miles that you would have driven, if you really kind of drove it a lot, might equal the distance between Earth and the moon. And 400,000 kilometers or 240,000 miles, those are big numbers to deal with. So often, astronomers like to use a shorthand based on light travel time. So as it turns out, light travels at a constant speed in the vacuum of space at about 300,000 kilometers per second, or about 186,000 miles per second. That means that we can use that as sort of a yardstick. And in the case of the distance between Earth and the moon, it's about a second and a half in terms of light travel time. It takes about a second and a half for light to travel from the moon to Earth, or vice versa. So when you look up at a full moon in the sky, you're seeing it as it was maybe a second and a half ago. And for comparison, let's go ahead and pull back farther from Earth, much farther from our International Space Station. And we'll actually see, again, Earth's orbit around the sun. And the sun comes into view in kind of the upper right-hand side of the image. And here you can see the 4 planets closest to the sun: Mercury, Venus, Earth, and Mars, the terrestrial planets. And Earth's distance to the sun is about 150 million kilometers, or 93 million miles. And in terms of light travel time, that's about 8.5 minutes. So you can compare that to the second and a half from Earth to the moon, or vice versa, which is kind of smaller than a pixel down here, or 8.5 minutes from the sun to Earth. In terms of light travel time, the comparison would be a second and a half is kind of like a pause in conversation, whereas 8.5 minutes, I don't know, might be enough for like a really quick lunch. If you really wolf down your Taco Bell or whatever, you might eat it that quickly. But the other distance that I want to mention here before we get too far away is the distance across the solar system. So we've pulled back again from the 4 terrestrial planets, the 4 Earth-like planets, Mercury, Venus, Earth, and Mars. We now see Jupiter, Saturn, Uranus, and Neptune, their orbits around the sun. And Neptune, from one side of Neptune's orbit to the other, takes light about 8 hours, a little bit less, but 8 hours to cross from one side of Neptune's orbit to the other. So the giant planets lying much farther away from the sun, and Neptune, the farthest planet of all, 8 hours from one side of the solar system to the other. If you want to think of a human equivalent to that, that's kind of like a good night's sleep. So a second and a half, pause in conversation from Earth to the moon, 8.5 minutes from Earth to the sun, or vice versa, quick lunch, 8 hours, a good night's sleep. Now, for comparison, the distance to the nearest star is 4 light years. So if you think about that, the difference between interplanetary distances in the scale of our solar system, at least as measured by the diameter of Neptune's orbit, is about a good night's sleep, whereas 4 light years to the nearest star, kind of typical of interstellar distances, is the equivalent of a high school or college education. So the stars are much, much farther away than the planets, which is a good reason why we have explored the solar system using robotic spacecraft. And although I would love to spend some time visiting various planets and introducing you to some of the spacecraft that have explored our solar system, instead, I'm going to just kind of give you a punchline here that, again, is a little bit more about the size of the universe around us. I'm going to put up the trajectory of not all of the spacecraft that we sent out into the universe, but the 5 fastest ones. These 5 spacecraft are traveling fast enough away from the sun to escape the sun's gravity, traveling at escape velocity from our solar system. And these 5 spacecraft, 4 of them were launched back in the 1970s. The 5th was launched in the early aughts. But they did flybys of various planets, or in the case of that one that was launched in the early 2000s, the dwarf planet Pluto. There were spacecraft designed to rapidly zip by objects learn as much as we can in a short time, and then continue on their trajectories away from the sun. So again, 4 of these launched in the 1970s. We have Pioneers 10 and 11, I believe, and then Voyagers 1 and 2, and then the New Horizons spacecraft. That was the one that was launched in 2000s to visit Pluto. But I'm going to pull a little bit farther away now, and I just want you to note that if you look at how far we're projecting the trajectories out to where those spacecraft are right now. And if you realize that Neptune's orbit is only about 8 light hours across, then you'll see that none of these spacecraft, even the ones that have been traveling for decades, well, all of them have been traveling for decades, basically, but even the ones that have been traveling since the 70s, none of them have traveled as far as light travels in a single day. So light travel time, although it's a useful yardstick, is vastly faster than the spacecraft that we send out into the universe. And these are the 5 fastest spacecraft we sent out to explore our solar system and are now moving beyond our solar system into interstellar space. So the way we learn about astronomical phenomena is not by using spacecraft. That's how we study our solar system and planets in our solar system and other objects in our solar system. But to understand the universe around us, we need to study light. And that is one thing that we're correcting now, actually, the brightness of the sun. We made it extra dim when we were close into it so that we could see the orbits of planets in the solar system. But now we're drawing it to be consistent with the brightness of the stars around us. And I'm actually going to change our perspective just a little bit here. If you've ever been to the Southern Hemisphere, you might recognize the Southern Cross. But we've traveled so far away from the sun now that you might notice, if you're good at your constellations, notice that Alpha Centauri, which happens to be the closest star to our sun, to our solar system, is kind of shifting in its position. Normally, it's kind of looks a little bit like that, about that distance from Beta Centauri, but we've traveled so far away that we're now seeing the parallax shift, this difference in perspective, because that distance, 4 light years from Earth, from our sun to the nearest star, is now a tiny distance compared to what we have traveled away from Earth and the ISS and the solar system. As we travel farther away, more stars kind of pull back from their locations, and the familiar constellations become disrupted by the new perspective that we have on the universe around us. And these are just the relatively bright stars that we see in our night sky. There are actually many stars that are much dimmer than this, and our interstellar neighborhood is sort of crowded with stars that are not quite as bright or may not appear in constellations. So, for example, I'm highlighting the locations of what we call brown dwarfs. These are sometimes called failed stars. That's a little unfair, and the people I know who study brown dwarfs tend not to use that slightly derogatory term. Instead, these are stars that are simply, well, are they stars? They're not stars, maybe. They're not really planets. They're a good example of how our human tendency to categorize objects and even people and things like that is not always accurate. Brown dwarfs kind of reside in this in-between zone between stars and planets. They're not large enough to fuse hydrogen in their cores, which is what we think of stars as doing all the time. But they're certainly bigger than planet-sized, and we know that they can, for example, burn a form of hydrogen called deuterium for short periods of time. So these are unusual objects. And the point I wanted to make here is that there are lots of stuff in space that's not necessarily showing up in every catalog that I show you. But again, what we've tried to do is add as much of the data that we can get on the universe around us into this 3-dimensional atlas of the universe. So let me go ahead and I'll turn off the brown dwarfs for now. But since I've mentioned planets, as we're kind of drifting here through interstellar space, I should also mention that around thousands of stars now we have discovered planets in orbit around them. So the circles here, these don't represent like orbits of planets or anything like that, but they're markers that show the locations of stars that have evidence of planets around them. So these thousands of stars that we're seeing here, each one of them may have just a single planet or multiple planets in orbit around them. And we've learned that through different means, through different ways of studying light from these stars. They show evidence of planets, sometimes by the spectrum of the stars, by breaking the light from the stars up into their constituent parts. We're able to see that stars are being sort of pulled on by the gravitational influence of planets in orbit around them. Or more often, and the vast majority of these have been discovered using what's called a transit method, where a planet much dimmer than its parent star passes in between us and the star, and we see a slight dimming in the brightness of the star. We can measure the size and orbital parameters of these planets through that way, through that mechanism. So these thousands of planets that we've discovered are really encouraging when we think about the potential for life in the universe. We don't think life resides on stars, for example, but we do know that Earth, the only place where we know life exists, has certain parameters that make it a pleasant place for us to live. We think of Earth as a habitable world based on its characteristics, its temperature, its size, etc. And so we're keen to find habitable worlds, whether that's potentially habitable or evidence for actual life on these planets. And this is the starting point. These thousands of stars with planets in orbit around them are where we can begin our search for the evidence of life in the universe around us. So this is a really encouraging data set because of these thousands of planets that we're seeing. I was kind of hoping that we'd have some of them come into view here, and indeed I did manage to do it. This large cluster of points that you see is from one mission called the Kepler mission, which performed that measurement that I mentioned earlier, looking for the dimming of light as from individual stars as planets pass in between us and the distant star. Kepler looked at more than 100,000 stars in search of the characteristic dimming from planets in orbit around them, and it managed to discover thousands of planets in just that small portion of the sky. So collectively, this amazing array of planets that are in many cases vastly different from Earth, but nonetheless individual worlds that we can study and learn more about, this large number of planets is encouraging as we begin to think about the possibility of life in the universe. And as long as we're kind of here at this location, let me go ahead and fade up one more kind of representational element. And that is what initially is going to appear as sort of a grid that crosses over the entire image. But as I continue to pull back, you'll see that this is actually a sphere. Our nickname for this is the radiosphere, centered on our solar system. And what it represents is the distance that our relatively strong radio signals have traveled out into the universe around us. So basically, television, radar, and in fact, residual emissions from nuclear explosions create a sufficiently strong radio signal to escape Earth's ionosphere. And we've been doing that kind of work in terms of emitting radio signals for about the past 80 years or so. So since the kind of 40s, or actually even sort of late 30s, is when we began to emit radio signals that were strong enough to escape our ionosphere and thus travel out into space. Now, because radio is a form of light, it travels at the speed of light. So over that period of 80 some odd years, it's filled, not really filled, but it's reached the outer limits of this sphere. And we can think of this as sort of our electromagnetic footprint in the universe around us. So if you think of those trajectories of the spacecraft that we saw earlier, close into our solar system, as the fastest nuts and bolts objects are kind of physical manifestation of our technology out in the universe around us. This is our electromagnetic footprint in the universe. It's a volume of space that represents our imprint on the universe. And if you can imagine being, say, a radio astronomer on a planet around one of the stars inside the radiosphere, you could point your telescope back at Earth and potentially measure the signals that we're emitting as an intelligent, perhaps intelligent in air quotes, species in the universe. So that's encouraging. But on the flip side, if you lived on one of the planets out here, outside the radiosphere, unfortunately, you're too far away. You simply wouldn't be able to detect radio signals from Earth, even if your telescope were pointed right at us, because you're too far away. The radio signals simply haven't had enough time to reach the objects, planets outside this radiosphere. So this is an interesting element, and I'm actually going to keep the radiosphere displayed as we continue our, I'm going to turn the radiosphere back on because I hit the wrong button. I'm going to keep the radiosphere displayed, and I'm going to go ahead and fade down our little exoplanet markers, because now I want to wrap up our show by leaving our galaxy behind and briefly introducing you to the intergalactic universe. We're traveling through interstellar space now. We've mapped out 100,000 some odd stars relatively close to home. Our radiosphere is receding into the distance. And as we pull back farther and farther, we're going to see that we reside in a collection of hundreds of billions of stars that we call our Milky Way galaxy. Now, the Milky Way is an object that you can see from Earth's surface. If you look up into a clear, dark sky, you can see a band of the Milky Way in our sky. And that's what our galaxy looks like from the inside. Our galaxy, the Milky Way galaxy, is a collection of hundreds of billions of stars. And if you want to know about how big it is from side to side, it's about 100,000 light years. So we started out by talking about the distance from Earth to the moon, 1.5 seconds in terms of light travel time. Brief pause in conversation. Quick meal from Earth to the sun or vice versa in terms of light travel time. A good night's sleep across our solar system, a high school or college education to the nearest star. Now, our technological history, a little less than a century of emitting radio signals into the universe, is just a few pixels on the screen. And 100,000 light years, that distance across the Milky Way galaxy. If you think about what humans were doing 100,000 years ago, we hadn't really left Africa yet. Our species was still confined to a single continent here on Earth. And so this 100,000 light years is, or 100,000 years in terms of light travel time, is roughly equivalent to the time scale that our species has existed on the planet. So these distances rapidly become quite mind-boggling, and they're going to get even more so as we travel farther away, because I really do want to hit just a couple punchlines as we travel farther and farther from home. Our Milky Way galaxy is actually a pretty good-sized galaxy. Hundreds of billions of stars is nothing to sneeze at. We have two satellite galaxies, the Large and Small Magellanic Clouds, which are basically in orbit around our own Milky Way galaxy. And what I want to point out is these little circles off in the distance are actually, again, markers that represent other galaxies. So whole other collections of stars with hundreds of billions, some of the larger ones, perhaps even 1 trillion stars, but many of these are actually much smaller. And each one of those dots is then a sort of city of stars comparable to our Milky Way. And as we pull farther and farther back, we're going to fade up more and more surveys of these objects, because it's actually challenging to find these objects and estimate their distances and so forth. And as we pull farther and farther back, what I want to draw your attention to is that the galaxies they're not uniformly distributed out in space. They sort of clump and cluster together. And a perfect example of that is this collection of dots in the upper right. That's the Virgo supercluster of galaxies. About 1,000, I'm sorry, well, it's a Virgo cluster. It's the center of the Virgo supercluster. The Virgo cluster contains about 1,000 galaxies, a much denser region of intergalactic space than our own local group of galaxies relatively close to home. I'm going to keep traveling farther and farther back, and I'm just going to use as a punchline now, as we travel farther from home, this challenge, but also this intriguing kind of benefit of light's finite speed as it travels through the universe, because it means that traveling out into, or looking out into space is also looking back into time, because we're traveling now so far from home, billions of light years from home, that the points that you see are galaxies that are in the past. As we look out into space, looking billions of light years away, we're seeing galaxies that they were billions of years ago. I also want to mention that you'll notice that there aren't many galaxies here or here. It's not that there are no galaxies. It's not that the universe is shaped like a big hourglass or bow tie, but rather that we just haven't finished our mapping project. We are still mapping galaxies. And again, it's a challenging process, but we've automated it, and we're doing it much faster than we used to. And as we continue our flight back away from Earth, away from the International Space Station where we started all this, you'll see the limits of different mapping projects as sort of wedges of mapped portions of the universe reaching out into space. And eventually we'll actually fade up these very distant little points that kind of blur together, especially through the magic of streaming video. And those are not even galaxies, but they're what we call quasars, the bright cores of young galaxies, very, very far from home. And in fact, so far away that we don't see quasars close to home. Quasars are an artifact of something that existed back in the early days of the universe. We don't even see them close to home. And I just want to end our voyage away from, so actually I do see a question here. What does a galaxy look like when everything dies? As you see, we see galaxies in the past. Well, so, I guess everything dies is an interesting phrase, because we know that galaxies evolve over time. Our own Milky Way galaxy doesn't look the same way today as it did in the past. And often it looks different because of interactions with other galaxies. Now, over time, and maybe this is what you're getting at with the question about dying, the universe will, and we're not really showing visuals that illustrate this. The universe is continuing to expand, and over time, we sometimes talk about the heat death of the universe, when everything is so far apart and sort of the universe has sort of cooled down that kind of nothing is happening anymore. And galaxies at that point, stars will potentially have died, and galaxies will become cold, kind of graveyards of stars. Galaxies, because they're gravitationally bound, will not really fly apart. They'll remain together as the universe itself expands, cools, and in at least one way of thinking of it, dies. But galaxies actually will sort of stick around. They won't glow the same way they do today, but galaxies are going to be with us in the universe pretty much until the end. But in fact, the punchline I was going to mention here at this point in the program is not about the end, but about the beginning, because what we're going to see as we pull far enough away is the punchline to this idea that light travels at a finite speed. You'll see in the background here, kind of this wallpaper in the universe is this, what we call the cosmic microwave background. This is not an image like a typical image. What this really is sort of a heat map. The bright parts of the cosmic microwave background correspond to hot parts of what turns out to be the early universe, and the dark parts correspond to cool parts. Now, here the punchline is that because we're looking so far out into space, we're looking so far back into time, we're looking at a baby picture of the universe, the earliest light that our telescopes can detect, not because of any limitation of our telescopes, but because the universe was too hot and dense before this light was emitted for light to travel any appreciable distance. So this is the youngest light, the oldest light from the youngest part of the universe's history that we can detect. So this dates back to an era when the universe was only a few 100,000 years old. The universe is now about 13.8 billion years old. So this baby picture is fascinating because it gives us a perspective on how that clumping and clustering of galaxies that I talked about a while ago, close to home, how that took shape. Because this baby picture shows that irregularity, that clumping that evolved into the structure that we see close to home. So we see the blueprint of our modern universe in this ancient light. Two things I want to mention before we head home. First of all, that variation in brightness from the bright parts to the dim parts correspond also to a variation in density. The dark parts are a little bit denser, the bright parts are a little less dense, and the temperature difference and the density difference is only 1 part in 100,000. These are tiny fluctuations. We've cranked up the contrast on this image. These tiny fluctuations in the matter and temperature distribution of the early universe gave rise to the clumps and clusters of galaxies that we see close to home. And finally, I just want to mention that it's a little deceptive. It looks like we are at the center of the universe because we're at the center of this three-dimensional image that I'm showing you. And it's true because we are the ones drawing the picture. We've plotted the distance of all of these objects away from us. So we end up at the center because we're the ones drawing the picture. We've simply plotted the distance of these objects away from home, away from us. So we end up at the center of this in the here and the now, even though the universe as we understand it doesn't really have a center. It's just because this map that we've drawn ends up with us at the center. So with that thought, I would like to go ahead and take us home. I'm just going to make sure that we have appropriately set our sights on the correct destination. So my computer helps me ensure that we're navigating correctly. And so I'm going to begin our flight home. And as we do, we're going to fade away that cosmic microwave background. We're going to fade away that baby picture of the universe. We're going to travel through those quasars, the unusual, dense, bright cores of young galaxies very, very far from home, and aspect of the early history of the universe. We're going to dive into these, what's sort of deceptively kind of a bow tie or hourglass-shaped collection of galaxies from our deepest surveys of the universe around us. And here it's very clear that the galaxies clump and cluster together. They're not uniformly distributed in space, but instead that blueprint of the structure of the universe that we saw in the cosmic microwave background has created the variation of density of galaxies and clumps and clusters of galaxies that we see close to home. We'll go ahead and fade down our last couple surveys. We have the Virgo cluster disappearing at the bottom of the screen as we get closer and closer to home. Can actually travel faster in Morrison Planetarium, but with streaming video, I don't want to take it too quickly. So we're going to continue our voyage through these individual points that represent distant galaxies. Again, each one of these points representing a galaxy, a collection of perhaps hundreds of billions of stars. And as we get close enough to our own Milky Way galaxy, you'll see the spiral structure of the hundreds of billions of hundreds of billions of stars that reside in our Milky Way galaxy. We'll travel past the core of the galaxy, disappearing to the top of the screen, and approach our radiosphere, that 80 some odd light year radius sphere that represents our most distant signals traveling out into the universe around us. I'll go ahead and fade down the radiosphere as we get closer to home. We're now traveling past the thousands of stars closest to our own sun. And as we get near enough to our parent star, the sun, a rather nondescript star in the scheme of things, will fade down the brightness of our home star to reveal the orbits of the planets around it, and then make our way down to the third rock from the sun, our own home planet Earth, as the sun sort of dims down to reveal the trajectories of our fastest spacecraft. It's a reminder of how far we've traveled out into the universe around us. I'll go ahead and bring those down as well to show just the orbits of our planets around the sun, past the giant planets, Neptune, Uranus, Saturn, and Jupiter, and then again, ending up where we began our show, the third rock from the sun, our own home planet, Earth. I was really happy to have at least one question pop up during the program. I hope I didn't miss others that popped up. I can get a little distracted sometimes. But if you ask any other questions in the chat, we're happy to answer them offline. But in the meantime, I hope you enjoyed this very quick tour of the universe from the International Space Station out to the cosmic microwave background. And we'll end our program here at the Earth. And I hope you have an enjoyable rest of your evening wherever you may be listening from. Thanks for joining us.